All right, we're going to wrap up the elevator action here real quick. And basically, what I need to do is take these two situations where the forces are unbalanced and then analyze them to figure out the acceleration of the object based on the unbalanced force. So our guiding thing here is the equation that you guys came up with out of the lab, which is to say the acceleration is equal to the unbalanced force divided by the mass. So I need the mass of this guy in kilograms, and I can just do that here. Your chemistry teachers probably taught you how to do this. 157 pounds in kg. It's 71-ish kilograms. So the guy's mass, 71 kilograms. And then we're going to need to do some converting. So yesterday we figured out that when the scale read 212, you have a force of 212 pounds up, smoosh poosh. You have 157 pounds down, gravitation still because his mass hasn't changed. So that gives you an FU of 55 pounds, and it's pointing up. Oh boy. Come on, stylus, hang in there. So I'm going to convert that into newtons. Let's see here. Oh, come on. You're going to do that for me? That's just sad. All right. Well, there's 4.448 newtons for 1 pound. Oh, man, the tip on this thing is just about to break off. That's going to get really sad. All right, 1 pound is 4.448 newtons. So I'm just going to set up a conversion factor. 55 pounds times 4.448 newtons for every 1 pound. Hey, let's see what that gives me. About 245 newtons. And then if I want the acceleration, I'm just going to take 245 newtons of FU divided by 71 kilograms of mass. And it's going to be something in the ballpark of 3. 3.45. That's newtons over kilograms. Mr. Arnold, that's not a unit for acceleration. Keep in mind, we talked about this in the lab the other day. The unit, the newton, is equivalent to a kilogram meter per second squared. So if I divide that by kilograms, I get left with meters per second squared. So there's my acceleration for the guy on the way up, 3.45 meters per second squared. I'm going to do that same thing for the situation where the scale read 122 pounds. So I've got 157 pounds down, and I've got 122 pounds up. When I go to draw this FU arrows aren't trying to balance out this diagram. If I wanted to balance this, I'd draw an arrow that pointed up. But this is not balanced. I want to show how not balanced it is. So that's why I'm drawing this fat arrow like this. It's going to begin at the beginning. It's going to end here at the end. Whoa. And that makes it the FU. And let's see, mental math. Is that 55? Again? No, that's not 55. That's not how math works, Mr. Harding. That's going to be... Sorry. Distracted. 35. There we go. All right, 35 pounds. So similar type of thing. I'm going to have to take that 35-pound FU and convert it into newtons. There's 4.448 newtons for 1 pound. So let's see here. 35 times 4.448, 156 newtons. So it's a little bit smaller unbalanced force here, 156 newtons. And again, I take that 156 Newton FU and divide it by, oh no. Ooh, pause. All right, I think I fixed it. So where were we? So we got 156 newtons here. We're dividing by 71 kilograms of mass. And you're not going to normally have to do these conversions, but this is just because I was taking some data that was in pounds. 156 newtons of FU, 71 kilograms of mass. That's going to give me an acceleration of 2.2. And again, I got this unit thing going on. I got newtons over kilograms. That's going to give me meters per second squared. So there's the acceleration when it gets to the top. Now, something to think about here. When the acceleration is 3.45, that was when the FU was up. Okay, the FU was up. Whoa. The FU was up, so the acceleration was up as well. The acceleration and the FU are always pointing in the same direction. Here where the scale reads less, I'm still moving upwards, but I'm slowing down. That's because my FU is pointing down here, so my acceleration is down. So think about that with a bowling ball. When you're trying to slow it down, you're directing your hits with the mallet opposite the direction it's moving. And that's the same type of idea here. The unbalanced force has to point opposite the direction of the motion in order for this thing to slow down. And so that's why we have this setup here where you have basically more force in the downward direction than you have up. That's going to leave you unbalanced by 35 pounds down. That gives you an acceleration down. So long story short, I technically should be calling this negative 2.2 meters per second squared because the direction of the acceleration is opposite the direction of motion. Motion's up, acceleration's down. All right. So we'll call that good there.